everyone, and thanks for the intro, Dan. I'm presenting Data Analytics Explained for Business Leaders, and the goal here really is to try to demystify data science, this overhyped and sexy topic that everyone seems to be talking about, and try to give business leaders a sense of what really is going on and how they can leverage it within their own businesses. So a little bit about me. I work at Cameron International. We're an oil and gas company as a data scientist combining a little bit of strategy, quant, and technology. I put up my LinkedIn and Twitter account there if you'd like to connect. And essentially the way I describe it to people is we move from knowledge to experience to data science. And, you know, jokingly, that means that I create little pictures of cats, and those are the root of all evil or opportunities inside the oil and gas industry. But really diving into the topic at hand, when I look at Gartner's 2014 hype cycle, I notice a handful of things that really jump out to me. And this was what sparked my interest in speaking on this topic, as well as writing some articles in this area. And what it is when you see data science, prescriptive analytics, big data, in-memory databases, the end value proposition that those pull out is really just accelerating decision making. And obviously there's technical sides to that, but the way a lot of business users see it is let's find a way to leverage data into more intelligent decision making. And the unfortunate part is we can't continue to rebrand this idea and not produce. And so hopefully we can come out and give business leaders a sense of what all of this means and how data science relates to the larger scheme of business. And so one of the things that comes out when you look into the analytics realm is the evolution that analytics exists as. You can move from descriptive to predictive, and then eventually to prescriptive. So hindsight, insight, foresight. And with each, we're reducing human effort, we're increasing the speed at which we can make decisions, and eventually delivering some value. So the question that I would pose to everyone is, where do you sit on that spectrum? And then how do we go from this high dollar value proposition that you see from a lot of consulting reports and industry oversight white papers to the other side, the actual technical depth? And the unfortunate truth is when you look out into the world and you try to research these topics, you see one of two things. You see the consulting reports, or you see on the very far other end of the spectrum these academic, esoteric research reports, and it's very difficult to get into the middle. And in both cases, they kind of point to this mythical data scientist to answer these questions. And so hopefully we can fill that gap in ever so slightly so you can bridge between the two. So one of the first things I like to start out explaining is regression. And the reason we start with this is it's kind of the basis of so many baby steps in the analytics direction. So using data to make decisions. Regression fundamentally allows you to take a number of points and just put a line to them. So set a line to a number of points. And there are a ton of different varieties that regression can come in. You can have different loss functions. You can have logistic versus linear versus Mars, all these different things. Simply to say there are a number of different areas where these can go, but fundamentally speaking, it's fitting a line to a set of points and understanding the impact that each one of those incoming variables has on your ultimate predictive outcome. The limitations of regression are fairly large, and something that I think that a lot of business users may not fully comprehend, because we hear this talk about causation and correlation, right? So if we look just intuitively at this picture, we see the Internet Explorer and the murder rate in the United States have a very interesting relationship here. And intuitively speaking, we know that as Internet Explorer's market share goes down, the murder rate does not go down, or vice versa. I mean, just in case, I do use Google Chrome, but theoretically this is not a causal relationship. We'll dive into this a little bit more in an example towards the end, but hopefully this gives you a little bit of an idea of the limitations of regression. The next phase I see is linear programming. Linear programming is an optimization method that tries to find the best solution given all these different constraints. So in this specific example, we're looking at the way to maximize profits given the production of tables and chairs. And so what it does is it essentially draws these feasible regions. So if all we did was create tables, we could produce 200 of them. And for each table that we don't produce, we can produce X number of chairs. And when we draw those lines, we end up finding this optimal point, the peak between the two. And that's the point at which we're maximizing profits. Now, the challenge you see here is is when those 2 points aren't necessarily full round numbers. So you see tables as 66.67 and chairs as 33.33. Unfortunately, we can't reasonably make that many chairs. No one wants to buy a third of a chair. So you would just push back to the nearest feasible point at that peak. So as a not so distant cousin, you have nonlinear programming, which is the same concept. You essentially feed in constraints saying we have this many production hours or we have this many man hours for these types of different processes. What is the profit maximizing or cost minimizing solution? And so nonlinear programming allows you to do these things in a non-linear fashion. So for each table you produce, it doesn't have to cost an additional 2 hours. You could model in economies of scale or things like this that may not be a one-for-one increase, so not a linear relationship. And so just looking at what those two things look like, you see linear relationship on the right-hand side, but the left graph, and then the nonlinear is a right-hand graph. So if you can take volume and match it directly to cost, or in a straight line, that's linear. If not a straight line, that's nonlinear. And again, on the left-hand side of this graph, something that we touched on earlier, if the blue line is our optimal feasible region, the red lines or the red dots would be those we can actually sell items, right? So we could sell 2 chairs and 2 tables. We couldn't sell 2.88 of either. So those are all solutions that you have when you know the incoming variables, but there are going to be cases when you don't know the incoming variables. You don't know what's going to happen in the future or what these things mean going forward. So an example in the oil and gas industry is what is going to be the price of oil? And we're learning the hard way that we made some assumptions that maybe weren't the most intelligent. We presumed things like $60 to $120. What a great world that would be. And today we're seeing things like $50. And so essentially, I'm trying to highlight the idea that each one of the assumptions that you make going into a Monte Carlo simulation propagates forward, as in each one of those little assumptions that's wrong collects into the aggregate error. But essentially, you can create these assumptions, you can create a distribution for them, and what that would look like is this a beta distribution? Is this, there are 2 options, A or B, and you would run a simulation, and each one of those values would be within one of your distributed distribution ranges, and then it would come together to give you some sort of solution or the most likely values and the cone of uncertainty. So when we look at these things, you would want to ask yourself, are we deriving our distributions from historical, or are we using just our best guess? And we should work as hard as we can to eliminate those best guesses and replace with a more intelligent way of doing business. So another area to look at, switching gears from Monte Carlo, are decision trees. Decision trees are phenomenal. They're easy to interpret. They make a great visual, and they allow you to route variables into different paths. And then you can predict the outcome of a variable based on where it lands in the final node. So here is a very rudimentary example, but it says, if we break down on color, we can go green, yellow, red, and we can break down its size, or based on shape. And eventually we can get to what we predict an individual fruit is. So if we just knew these incoming variables, we didn't know what it was or what fruit it was, you could have theoretically used these to get to that conclusion. And obviously you can do the same thing with different types of variables or different types of data. One of the challenges with a lot of these methods, particularly decision trees, is overfitting. And so one of the things that data science needs to be very, very careful of is making sure they don't overfit, and the way you do that is set aside half of your data or a percentage of your data into a test set. So you would essentially build your model using 70, 50, whatever percentage of your data to build the model, and then go through and get accuracy statistics on the test sample. And what you're seeing here is that red line shows that at a certain point you go from very, very low error or very, very high accuracy, and it starts picking back up again. And so this would suggest that the best point to use is sort of that low or that bottom valley point on our test sample line. And that would be the optimal size tree. So moving away from decision trees, another area that I think is really neat is k-nearest neighbor. And so what k-nearest neighbor does is it takes in a bunch of incoming data. In this case, let's say we're looking at red triangles or people who didn't buy from us. So people we had the potential to sell to and it didn't work. And then we have our blue squares, the people who did buy. And k-nearest neighbor can predict, based on a new person. We'll say that is our green dot man. What is he going to do? Is he a buyer or a not buyer? And the first question we have to answer is, what is K? So K, if it equals 3, we're looking at that inner circle, that inner purple circle. And so we would see, okay, within that circle, there are 2 non-buyers, 1 buyer. And so we would say, this is not a buyer. And then if we expand it out to the larger black circle with a K equals 5, we could say, okay, well now we see 2 buyers and 2 non-buyers. What do we do? That's almost a toss-up. Well, there are a number of different things you can program into a k-nearest neighbor algorithm. You can say something like, those customers that are most closely resemblant, those who are closest to green dot man, weight those more heavily than those blue dots way over there. And so you could output something like the probability or the propensity that you believe green dot man will become a customer. And that is incredibly informative. So you can say, we believe with this percentage that he will convert or will not convert. What is the value potential of all that? I mean, it sounds interesting, it sounds great. Well, what if you have variables that aren't inherently related to one another? When you go on Amazon, say you buy this wolf t-shirt, which, by the way, I highlight because it has some very hysterical reviews. But anyway, say you buy this wolf t-shirt, you buy this super nerdy predictive analytics book, you buy this pocket protector and this poster. Inherently, we could group this all into, say, a customer segment of nerds, or we could use k-nearest neighbor, and we could find the people who have also purchased those exact same items. And we could recommend to you the items that you haven't purchased, that those people so very similar to you have. That is an incredible opportunity to bring product discovery forward. And more importantly, no longer are you recommending, oh, here's a pocket protector in blue. You know, a pocket protector that's costing $6, $7. You could say, out of the other people who also bought these things, there's a consistent theme of buying a drone. And suddenly you move from a $6 item to a $1,000 item. And so the profit potentials here are massive, and it really opens up a different way of looking at things. The challenge is you are computing the distance between all of these incoming points, which becomes very computationally challenging. So much like k-nearest neighbor is the idea of clustering, and something that I mentioned just a second ago. So if we were to look at, we want to know what customer segments are. We want to take our incoming data, we'll plot it into a multidimensional space, and we'll say, what are some natural groupings based on, say, age, income, gender, all these things of people? Where could we say these people fall? And based on how your algorithm groups them, you could take that back and you could look at things like the median income or the average age, things like this, and you could answer questions like, for this particular customer segment, we should target them with this most likely purchase product. And you can start developing and targeting marketing at people with a great understanding of what their needs are, and you can make those predictions even if you've never seen the person before, or things like that. And the reason that I focus on these marketing examples is because they're fairly easy to comprehend. Buy, not buy, people get those things. But there's nothing to say that this is a marketing-focused realm. Ultimately, these data models don't care where it comes from, where your inputs are coming from, where the data is. It just eats whatever you throw at it, right? So, like I said, you could develop these clusters and eventually say, based on these, what is the propensity for us to convert in a given segment, or what's our most profitable group, and how can we target more people like that? That's ultimately one of the most common use cases of clustering. Beyond clustering, we look at Ensemble, and Ensemble is this thing that makes such intuitive sense, but it took a while for people to come around to saying this is what we should be doing. What Ensemble does is you could create a k-nearest neighbor model, a regression model, all these things, and then average them together. You could say our k-nearest neighbor says that Bob is 92% likely to buy, and our regression model is, say a logistic regression is saying it's 67%. And when we average those two together, in theory, we're going to get much better results. And the reason is because each time you bring in a new model, they have biases and they have variance. And in theory, when you average together these different methodologies, the biases balance one another out. So you get towards a better version of truth. And we've seen this work tremendously across a vast number of different domains. So again, even if you're not doing anything new, you can just average the techniques that you already understand. An example of an ensemble that I think is really phenomenal is an ensemble regression decision tree. And so essentially, you'll create a decision tree, and your data will flow down to the end leaf nodes. And the way a decision tree would work normally is you would say, everyone in this node is going to buy. We predict that these are buyers. Well, once you fit a regression line inside of that, you could say, okay, now we believe that Bill has a 92% chance of buying. We believe that Fred has an 88 and Mary has a 99. Those are incredibly valuable because now you're getting a granularity to these people. So if you do need to prioritize, you're going to hit Mary at 99, then Bill at 92, and then Fred at 88. The other thing is, an ensemble regression tree creates a number of different regression trees. So you could create 50 different regression trees, randomize how the decision tree gets built. And so now you have 50 different predictions for every single incoming data point. And this sounds computationally exhaustive, but it's not, because each one of these is developed independently. So you can develop one decision tree and regression equation on at one time and just keep sending them through. It's really phenomenal in the ensemble realm to do these sort of things because the computational complexity isn't nearly as large as some of the other advanced methods. Another example of ensemble is Adaboost. Adaboost I find quite funny because it makes me think of nerdy people. It essentially takes a bunch of very weak classifiers, so variables that didn't do much originally, that weren't weighted very heavily or that didn't have a real impact on your end result, and combines them. So let's say we're looking at these 7 incoming variables, and we see that each one of these lines doesn't do a really good job of predicting people. Let's say we're trying to get all the little circles on one side of the line, and we're trying to get the squares on another. Each one of those incoming 7 doesn't do a very good job. But when you combine across those and you create that jagged line, suddenly you're separating your buyers and non-buyers perfectly. And so that's the idea behind Adaboost. And the reason that I find this funny is it's taking weak people and combining them together. It's the transformer of data science. But again, it's just the intuition behind this. It's actually there, right? These aren't black box or voodoo math methods. So something to just be aware of. And when we move towards the real bleeding edge of data science, you see things like SVM. SVM is counterintuitive. Honestly, it is quite hard to understand from a math side alone. I would be very sad for someone trying to just dive into the math and understand what's going on. But the way I've seen it explained, this actually comes from Reddit. So full credit where it is due. But there was a Reddit post about this that essentially broke buyers and non-buyers into 2 different segments, and it fit a line. So we see here that this line sits directly in between the red and the blue. Okay, so on the bottom of the line, the red are pretty close, and on the top of the line, the blue is pretty close. Okay, but technically speaking, the 2 are separated. So when we go to predict, what happens? Well, with that specific line, we'll see something like this. We'll see we get 90% of them right, but then this one little red dot falls on the wrong side. So we predicted that they weren't buyers. Or we predicted that they were buyers because it's on the blue side of the line. But they did not convert. They did not become buyers. So we targeted them with an advertising campaign. We reached out to them. We did all these things, and it didn't result in a sale. So overall, the accuracy is pretty good, but we can do better. So what does SVM do? SVM takes our original line and it tilts it ever so slightly, and it does what's called maximizing the margin between the 2. And in the background, it's taking all these points, it's projecting them into a higher dimensional space, and it's slicing them with a hyperplane. That is incredibly complicated. All you need to know is it's maximizing the distance between this line to improve the predictive performance. So the results of that are something like this. Now that line doesn't skew towards the red dots, and suddenly that red dot falls on its right side. And so that small increase in predictive performance results in huge gains when we go to scale. When we do these things across thousands or millions of customers, that results in massive marketing cost savings or whatever your application is. It could be, where are we drilling for oil, right? And if we get 10 feet in the right direction, that's millions of dollars saved in drilling cost. And so SVM is one of these methodologies that is really bleeding edge, and it's incredibly difficult to understand, but it learns rapidly from data, and it takes in a great deal of information quickly. And so this really illustrates what we're doing when we're projecting it into a higher dimensional space. So we're taking these 2 and slicing them. So intuitively speaking, this makes sense, right? Now we have these blue and these red, and we've maximized that hyperplane between them. But when you have somebody come in and tell you, oh, we're going to project data into different higher dimensional space and chop it with a hyperplane, most people want to run away and hide because that wasn't a very fun class in college, right? So hopefully this demystifies a little bit of that. Another area that's very cutting edge, or really this was developed decades ago, but only now are neural networks really coming to pass. Only now are these methods coming to pass because the computational time and the cost of computing has dropped so immensely. So essentially, it creates a number of hidden layers, and it's trying to replicate the logic of the human brain. So you'll pass in these inputs, and then it will create these hidden layers, and eventually your output. The beauty of neural networks is it does things that are incredibly difficult to do in normal programming or normal data science settings. It can create this immensely complex logic that's almost impossible to build in traditional programming, and it will learn and adapt from new information. So we see applications in handwriting recognition, IBM Watson, and speech recognition, things that you need to be able to adapt to dialects. You need to be able to adapt to this person seems to skew every letter a little bit to the left and still come out with the right answer. These are the areas that are really, really exciting because it's moving us towards that idea of artificial intelligence or machine learning type domains. And really on the bleeding edge of that, this artificial intelligence, whatever you want to call it, is coming out in the form of deep learning. And deep learning, an example that comes out of Google is they took this immense amount of computers, incomprehensibly large, and threw YouTube videos at it, and eventually, without labeling them, without telling them, here's what's in the photo, here are these things, it would go through the photos and eventually recognize patterns that consistently occurred in videos and in the images coming at them, or in this case, images. And eventually, they noticed that it was able to recognize or identify the pattern behind the human face. And on the right-hand side, you see a cat's face. Now, this may speak volumes to the number of cat videos that are on YouTube, but the concept and the ability to do these things is really revolutionary. And so where is this applicable in the real world? What can we do with these things? And so there was a very interesting competition that took place in Germany a few years back, and the competition was, can you identify accurately what the numbers on someone's home are, the address. This is a challenge that Google runs into when they take photos on the front side of people's homes and then parsing through those at scale to identify what those address or house numbers are. And so they had human beings go through all these images and classify what the numbers were. And they came out at 98.5% accuracy, whereas the top performing algorithm came out with 99.4% accuracy. So this was an example of a time when computers exceeded the ability of human beings, and not only in speed, but in accuracy, and in a realm that humans are supposed to be very, very good at. We're supposed to be able to look at something and discern the information that comes in. Computers, historically speaking, you had to feed them things. You had to give it to them in a very clean, structured format. This is exceptionally unstructured, and still the computer was able to beat humans. So an exciting view of the progress of deep learning and artificial intelligence. So when we look at what does this process really look like? What does data science look like operationally in a company? I want to take a moment to do an example of a regression and then data transformation. So hopefully this will give you some idea of this isn't some pseudoscience, this isn't incomprehensible. And if you get the right people who can tell you the story, that can convert data into stories, you can bring forth a number of insights and understanding of your business at a granularity that simply hasn't occurred before. So take this particular analysis with a grain of salt, because it is meant to be, to some degree, humorous, as well as bring forth an example of how to do these things. But we'll see. So I did an analysis of, do I create value? Do I do things that are good for the company? So I looked at the stock price over the past 90 days, or this was before the end of the year, so 90 days looking at it. And so if you were just to plot these two lines, so with each day my line increases by 1 and the stock price is the adjusted closing price over the course of that same period, what's happening? Intuitively speaking, it doesn't look like there's any relationship between these two. It looks like this line is the orange line, number of days worked goes up, stock price, it seems to be going up, down, all these little things. But that isn't science. That's visualization. And yes, there is intuition that can occur here, but they don't sit in silos. They need to be combined. So what can we do to combine these two? Well, we can regress one across the other. So let's see how much value do I create in a normal day. And the results of that are here. So essentially, we see that the R squared is quite good. We see 0.88, so that would suggest that we can explain 88% of the variability of stock price based on the number of days that I worked. So I impact 88% of stock price. Now that's phenomenal. I'm making a difference. Unfortunately, it looks like I cost about 30 cents a day. So for every day that I work, I'm decreasing stock price by 30 cents. I think that's a heck of a deal. I thought I was getting paid a lot more than that. But the problem is, now we ask ourselves, okay, but how many shares are there? And for Cameron, it's 197.45 million. So when we put that out to scale, that would suggest that I cost $58,587,364 per day. So obviously, it's now my job to figure out how do we change this result, right? How do we, quote unquote, transform the data to hide this? And that's really the humorous prerogative of this initial analysis. So one thing we can do is we could scale stock price. We could take the day's minimum, that specific day's price, subtract it from the minimum over the course of the 90 days, and then divide it by the maximum minus the minimum. Maximum minus the minimum simply gives us the spread of data. So what is the difference between the max and the min? That is the range of variability that occurs within this time frame. And so when we do that, clearly there is no relationship. We've eliminated it completely. Now the orange line goes up, and who the hell cares what the blue line's doing? You can barely see it. Unfortunately, and I hope that when you see this, you go, this isn't right, right? Intuitively speaking, you can't just transform that and say that it has gone away. So I understand that. So let's go ahead and let's scale the 90 days as well. So let's put it on that 0 to 1 basis that we've done with stock price. And so now we see we've just taken the exact same data and we've plotted them in the equivalent range. And so now it kind of looks like there might be a relationship, right? So as one goes down, the other goes up, or as one goes up, the other goes down. But it's still hard to discern what's really going on here. So I guess we should take the orange line, the number of days worked, and get it to start up at that 1 and get it to end at that 0. In other words, get them to go in the same direction. When we do that, this is the plot that we get. And so when we see this visual, it makes a heck of a lot more sense that the regression came out with 0.88 as the amount that I impacted variability, right? So as we see this line, they're now going in the same direction. We've controlled for scale. We've gotten 2 vectors or 2 columns of relative magnitude. We've scaled them and we put them in the same direction. And that's the technical side of things. But really what we've done is we've taken a relationship that always existed there. We've taken that and brought it forward. We'd allow that insight to bubble up in a way that is intuitively appealing. Now, when we take a step back and we ask ourselves, is there any way that he could actually do this over the course of 90 days? Well, no. Cameron operates in the oil and gas industry, and so the third unknown variable here is, or unseen within this analysis, is the dropping price of oil, right? And that's causing stock price to go down. And there may be some minor impact of my employment, but certainly it's not $60 million a day or so. So that's what's to understand, is every time you see one of these things, there is a role for intuition, and there is the need for business managers to really come back at analysis that's coming in and say, well, what about this? What about these things? Just giving things the smell test. And fortunately, when we do that, the relationship of my employment is almost non-existent. And really, it's most likely capturing some other variables beyond the price of oil. But just something to be aware of, and to see that there's a very important reason to look at causation versus correlation. And so as we think about what we've just done, you may be sitting back there and asking yourself, what in the hell kind of voodoo math did he just do? he scaled, he inverted, he flipped this data, we looked at it one way, and then it became this intuitive visual. How can you do those things? And this is something, these are questions that I get all the time, right? So I've really racked my brain of how do I explain this in a way to illustrate that you can take one piece of data or one data cube or one vector and you can do scaling maneuvers, you can transform it in such a way that you don't lose any information, but you can create a more powerful and intuitive visual. And so kind of pioneering this explanation with you guys, would love to get your feedback on whether or not it makes any sense, but here's what I've come up with. So right now, last night I was sitting in front of Google Maps and I looked up a route from Houston to New York. And believe it or not, it's on this Earth, this picture of the globe. It is plotted in that space, but you can't see it, right? So we are looking at a very, very bad perspective of this data. But I promise you that the route exists. So what can we do? In the same way that we converted that data, in the same way that we transformed what we were looking at, we can turn the globe. And we can see, okay, well, it does exist. I can't say too much about it. It's not very insightful as to where I should turn or what I should do. So what else can we do to it? Well, we could zoom in. And right now we're looking at it and we can discern, okay, there are some movements that we need to look for, all of these things, right? We can see how long it's going to take. Very, very necessary things in order to make this specific piece of data actionable. But at the same time, Florida is pointing upward. We have our essentially our compass and our scale misaligned with our intuitive understanding of this. So what else can we do? Well, now we're looking at it from a slightly different angle, but we're getting ever so closer to transforming it and shifting our perspective in such a way that it makes intuitive sense. And so here we are. Now all we've done is we've taken the planet, we've rotated it ever so slightly, we've taken this three-dimensional object, and we've rotated it in a multi-dimensional space. We've zoomed in on what's relevant to us. We've taken it out, we've highlighted it. But at each one of these points, each time we made a maneuver, the route was exactly the same. The route has not changed with each one of those maneuvers. And that's the exact same principle. When I was working with stock price, that line, believe it or not, had we zoomed in at when the blue line was just barely above the very, very bottom. So when we had the 1 to 90 orange line and the very small blue line at the bottom. The line in and of itself had all the little grooves and ridges and movements that it had before, just at a much smaller scale. And as long as we keep in mind what the scale is and the things that we've done to it, and in a map you understand those things because you can see where the compass is. We always know how we get back to north. We always know what the scale is. How far is 1 inch on this map? And that's all we're doing when we create these more intuitive visuals. And that is the power of data science. You're not just visualizing things. You're really getting a much deeper understanding of what's going on. And so the idea here is in the same way that we would take a cube, we can turn, we can invert, we can do all these things. The geometry, the difference between one point and another is still exactly the same. The units in the difference between those two may have changed, but the data itself is exactly the same. We are just turning it and moving it in such a way that we're creating an interesting or insightful perspective for us to look at. So I hope this gives you a little bit of idea, for one, the need for the nerds, the need to convert data to analysis and eventually tell a story that's intuitive in a way that will allow you to unlock business value. But also that this isn't some sort of crazy, incomprehensible science. It's the evolution of really fast computing, a measurement of almost everything, and bringing all of that together and understanding the interrelationships between all of these different variables. And what's exceptionally exciting today is we have these universal variables that we can relate on. What do I mean by universal variable? Well, you can get data sets that relate on time. You can get weather patterns, and when you can connect the day that a weather occurrence happened to the day that your stock price, or the day that all of these different variables occur, and suddenly we can interrelate these data sets. And there are so many public domain pieces of data as well as sensor data that we can relate on that variable. Another would be latitude and longitude. We can now say these two occurred very close to one another in the space or in the world, and we can say we align, people saying these things on Twitter with revolutions in this part of the world, things like that. And we can get down to these universal variables. And I mention that because as you look towards building up an enterprise or scalable solution for analytics, hunt out those universal variables where I can take this piece of information and I can hand it to someone outside of my company or in a different industry, and it still means something to them. I'm not going to put in a state or a sales district or something like that. I'm going to put in latitude and longitude or a real date. And so I hope this was a little bit informative and opened up maybe some questions or ideas of how you could leverage analytics at your own company or to answer some questions that you have. But keep in mind the concepts are universal. You can apply clustering to all sorts of different things, and in most cases you can manipulate your data in such a way that you can get it to fit into one of these primary methodologies. And then if none of those work all that well, ensemble them, right? So that's essentially the intuition behind some of these processes. So if there are any questions or anything, I would love to open it up.
All right. Well, thank you, Alex. That was great. A lot of great information. I love some of that. So we don't get to thank you for bringing the price of oil down, or?
I might not be employed very long if that was the truth.
Cheaper prices at the pump.
Right, right. I'll take credit, but I don't think I did anything.
Not good for your industry, though.
Right, right.
Yeah, I love the smell test and the voodoo math. That's what I think of some of this business analytics sometimes, the voodoo math.
Oh, sure. And, you know, sometimes you go into old reports or the way people have been doing this for things, and it's like, well, this is voodoo math, right? So this is just, you know, the process of trying to uncover some interesting insights from what's already existing in your data. So hopefully that was the takeaway.
Yes. All right, let me see here. Where did my questions go? There are some questions.
Okay.
Where did they disappear to? All right, so my first question here is what types of tools do you use for your analytics?
Sure. Well, I actually wrote a post about this pretty recently of the top 10 tools for business people out there on LinkedIn, but I think that data science in general is really shifting the focus away from, say, paid tools. So I use a lot of R, which is just an open source data analysis software. It's hyper scalable, good bit of Python. KNIME is another platform/tool. KNIME I would recommend for people starting out, trying to get their feet wet with some of these methods. It's fairly scalable, and it's an open source platform that allows for visual programming. So you use nodes rather than hard coding. So you'll just drag and drop a node, you can double click on it, and it'll open up a GUI so you can say, okay, I want to filter on this value, or I want to do these sort of things. And you can, you know, flip, pivot, all these things to your data. And what's really, really phenomenal is you're not doing this in Excel. You're not doing this in a way that you're changing the underlying data. KNIME references a file on your desktop, it makes all these changes, and you can output it to a new file, but it never hurts or changes or manipulates your actual underlying data. And so that's just a really good practice when you move into some of these things. And the other thing I would say with tools is there is always going to be a use for these traditional relational databases, or at least in the near future / the rest of our existing careers, right? So that's just a fact in the sense that you can go back to, there are still companies with the old IBM mainframes and all those things. But I would focus on this open source, give them a shot if you're not looking at them right now, and be willing to open up things that maybe weren't something you had gone to before. So SAS is one area. It's just, when you look at the macro trends, the development speed that a lot of people work at requires writing custom algorithms or writing custom code, and there's a really phenomenal data science community that open sources a lot of those things that they build. And those get put into open source projects much, much more quickly than they do into, you know, the existing frameworks of, here's this company that builds these tools. So I hope that that was somewhat informative.
Yes, and as another follow-up with that, someone was talking about your favorite tools. They were just commenting that they use Power Query to mash up data. Is there anything that you use currently to mash up data?
Sure. You know, whenever it's easy or not too large. So in the context of normal everyday work, I find that there are some really interesting tools out there that would help you with, I guess you can call it data cleansing or data smashing. One is OpenRefine, and what OpenRefine does is it has text similarity functions that allow you to combine data sets, and it makes sort of a best guess of, are these the same entity? So you can take things like your existing it takes things, sorry, I think I paused screen sharing or something. So it takes things like your existing naming conventions and say, I used this recently for combining country names from risk factors and the country names that things are shipped to, and you'd see things like Saudi Arabia misspelled, or some people are just calling it Saudi, and it's finding those underlying text relationships and combining them. And so that was something that I think really accelerates a really dirty way of doing analysis, which is combining text fields. But in some cases, that's all you have. And so be open to these sort of tools that can accelerate. And I know within Excel, some of those newer add-ins are trying to address those exact things. So hopefully that's one area. And then also KNIME has some really phenomenal things that do things like text similarity search. And so I try to think that we can combine on text, but combining on number is something that always makes me pretty nervous because if they're two different numbers, I like to think that there's a reason for that. So anyway.
All right, we had a couple people thanking you for the content, that it was perfect and well done.
Sure, great.
Couple wows. And someone was inquiring, they currently use Excel as their main tool. If they were to migrate to one of these other tools, like say start using RStudio or the KNIME,
sure.
Where would they go to get some introductions into these tools and how to use them? Do you have any recommendations?
Sure. So honestly, I'm saying KNIME. I primarily use that. There's also a tool called RapidMiner. They're highly complementary. If you know one, you can pick up the other in a handful of minutes. But both of those tools, again, node-based frameworks. So you'll go to your node repository, they're calling it, but it's really just a number of different things where you can pull, say, an Excel sheet to be able to do analysis. And you would just look in your node repository, and it's all fairly organized. I picked it up just doing it myself. I had the option of doing things in R. I was like, okay, well, this would take about 50 lines of code, but I just really don't feel like doing that. This isn't that complicated. I don't want to crank up this and have to code and deal with, this isn't compiling or I'm getting all these errors. And so KNIME was a really, really elegant solution that saved me a lot of time and headaches. And it was something that I just picked up. But when you download either one of the tools, they have tutorials that come in with it, and both of them have a fairly strong community behind them. I'm always very surprised, whether it be KNIME, RapidMiner, recently even Tableau, you put a question out there and there's these people that are ravenous, are very passionate about data, and they want to come out there and help you. So don't think that this is something that you can't do. In fact, I think you'll look back after you pick one of these up or do one analysis and you'll go, I don't know how I got through life without this. Dragging and dropping and pulling equations down and all these things, there's just a lot of ways that can go wrong, and KNIME and RapidMiner help to fill that gap of someone who wants to be hyper analytical or much a better analyst than they maybe are now, and do it in a way that isn't going to require them to pick up an immense amount of deep skills. So that would be my recommendation.
Great, thank you. Someone else said that they currently use like Crystal Reports for their enterprise reporting tool. They're kind of wondering what type of recommendations you might have for other alternative options.
Sure. I think that like many companies, once you get to a certain scale, there's always going to be a role for the SAP tools or these enterprise systems. And it's really just answering which one makes the most sense. Is this going to be a report that we need to answer a really, really important question on? Do we need to do really deep analysis? Or is a visual of, sales over the quarter gonna suffice? And so I think that there will always be this, or at least in the near term, always be this role for these tools that do this and are able to scale out to the entire company. For me personally, the tool that I use that isn't open source, with the exception of Microsoft Office, is Tableau. And not to say that there's any reason that I use that over one over another, but I think it's quite intuitive. It creates really great visuals, and when you can automate out a lot of the report creation. But the tool isn't necessarily going to solve all your problems or create a better world. In fact, if you've ever tried to put a new tool in for an enterprise or put a new tool in to do something, it's a heck of a pain. So if you can just use your existing stuff and create something that's a little more intuitive or things like that, I think you might be surprised what's possible. So
great. Someone just one clarification. You mentioned a data cleansing application. What was that name again?
Sure. OpenRefine, and there's also some of that functionality within KNIME and RapidMiner, but OpenRefine is a super lightweight application. It opens up inside your browser, and you can import CSV, Excel files, just flat files, and it goes through. It has a bunch of different algorithms. If you go to Edit Columns, you can go to that and do clustering and editing, and it'll bring together a bunch of things that it thinks, okay, here's Alex.Jones, here's Alex Jones, here's Alex space Jones. Well, if you did a VLOOKUP on those things, they wouldn't connect. And this brings them all and it says, hey, we think this is all the same thing. Do you want to name them the same thing? And you can say, I just want this to be Alex Jones. And then you hit merge, and it writes over all that dirty data. So another thing to know, if you do go into OpenRefine, always copy your original data source, so you can do that inner join between the two. So you can essentially do a VLOOKUP on the dirty data to the clean data, and so on. It's a very great tool when you have sort of a smaller data set that you need to clean up, and you have those text strings. So.
Great. Just to wrap up, do you have any like websites or references that you could provide the attendees as far as areas to go to find more information about data analytics?
Sure. I dropped my LinkedIn in there every so often. I'd say once a week I post something that I find interesting or helpful, and I try to write on that topic area. I keep an eye on kdnuggets.com, Data Science Central. Both of those are good resources. And they're putting stuff out that's relatively technical, but I can't say that there's anybody producing really great content all the time. So for your given application, if you want crystal reports, you're going to go to a different user forum than you would for KNIME and so on. So unfortunately, there isn't a catch-all. It's just the early stages of analytics, and there isn't somebody who has a corner on the market. But go out there, look, and find something that's most relevant. But if you have a specific tool that you're looking for help on or that I've mentioned, feel free to reach out to me on LinkedIn or something, and I can possibly point you in the right direction.
Great. Are there any hot topics for 2015 that people in the business analytics area should be focused on?
I think that a lot of the topics that were in Gartner's hype cycle, a lot of companies are now getting into the depths of trying to implement. Within oil and gas, the joke is that we focus on geology, and the world moves at a geological pace, and by extension the industry moves at a geological pace. So some of the things that are normal at other companies we're trying to sprint to get done, but I think in a macro sense it's trying to consume and really understand this immense amount of data. So companies now have things coming off of sensors, and a lot of that goes into this massive repository, and you don't do anything with it. And the reason is after 89 million rows, nobody knows how to do anything. So you have to hit that with some specialized applications and be really thoughtful of how to even do that analysis. And of course, there's a lot of ways that can go wrong. But I would say companies will begin to develop this really deep understanding of how do we handle things that don't fit into Excel, that are beyond this 1 million row limit or whatever you might think is this prohibitive area where you're like, you get a little scared of how am I going to do this. And so I think we'll see more people get comfortable with these open source tools and maybe do things outside of, okay, well, I'll just keep limiting my query down, but really ask it across the entire data set and begin to develop the understanding and skill set behind those tools that enable them to do that. So.
Great. Well, thank you very much, Alex. I appreciate you taking the time to present this material. It was outstanding. A lot of great feedback from our community. And just a
Super.
reminder to all the attendees that there will be a short survey. If you would please take the time to complete that once you close out. Any last words of wisdom, Alex?
You know, it's not as hard as you think. You can get out there. You know, it's all math. It's not that intimidating. Plus, minus, divide, multiply. It all comes down to those things. So.
Great. Well, thank you very much, Alex. Have a great day, everyone. Appreciate it.